Hello. Can you hear me now? I'm seeing something actually respond, but you're probably getting a little bit of background noise from the fan of the machine that I'm currently burning. But can you, yeah, you can hear? Oh, hey, woohoo! Sorry guys, thank you for your patience. No, I'm not going to add the background noise of the video stream. Sorry, the SoundCloud stuff off the back of this. So I'll just have to deal with listening to my dulcet tones, I'm afraid. But like I said, thanks for your patience. Sorry about that. For some reason, the microphone's not behaving as I would expect it to. I'm going to start up a couple of boxing. Yeah, whatever. Go away. Okay. Alrighty, so I'm just spinning up some VMs and I'm going to start recording as well, because hopefully this second part will also capture nicely for those people who are not able to view it in real time. So it's also being saved on Twitch, but I'm saving it locally too. Cheers to shells. Okay, now, so as you can see, what I've done here is I've got my MSF set up locally with the following changes, and I did this for a couple of reasons. By the time I finish this, I'm actually going to submit a pull request while you guys are watching, so so it actually does get included. First thing to note is these files here, the kernel.c, kernel.h, and windefs, they're all the helper functions that I use to do token-related and kernel-related stuff. Just as you saw when we were doing the exploit standalone, all of those functions are in there. Yeah, I know the mic is strange/loud and you can hear the backdrop, but I'm sorry, it's not going to get much better because Linux. So I'm afraid you'll have to deal with it. Anyway, so that's what those three files there are. We're not going to dive into the source of those. We'll worry about those another day if you're interested. Excuse me. This make.ms build is let me show you. This is just an XML file that automates the MS build process for the new binary that we're going to be using that will conduct the exploit. There's nothing particularly interested in here, but because I am meticulous and I like to make sure that I've got all of my I's dotted and T's crossed when I submit things like this to Metasploit, this build file here is what gets wired into this make.bat. So if we go git diff, we can see here that I've added a new build step here that says go and build the CAPCOM.SYS driver exec exploit. So all I'm doing is I'm kind of doing all the MSFE related automated build bits and pieces, and I did that outside of the context of this stream because I didn't think you would find it very interesting. So that's what that file's for. Git ignore, well, you know what a git ignore file is, it's just ignoring a bunch of stuff. And I've taken the liberty of creating a new Visual Studio solution and project and stub C file. The C file is literally just a stub, which contains some bits and pieces that are required to wire it in as far as exploitation is concerned. You'll notice that there's no actual MSF module here because we haven't written it yet. So what we're going to do first is we're going to dive into the C and we're going to rewrite the C to fit the MSF approach because that's probably the most interesting. And I am going to handcraft most of it again. I have got a reference here on screen, so it won't be that painful. I've got this machine here, this Corlan Win7 box. You can see that I've done a bit of Corlan related bits and pieces in my time, and I've been using this for exploit dev on Corlan. This one this time I'm going to be using it as the victim machine, but we don't need to look into that just yet. Here is my fairly classic dev environment for Meterpreter related shenanigans. And so let's just have a look at the stub. I'm going to give you a quick rundown on the bits and pieces that are required to make this function correctly under the context of a Meterpreter session. So the way things work, when you run a local privilege escalation exploit in Metasploit, first of all, you need an existing Meterpreter session, because the local privilege escalation exploit actually interacts with the existing session that's not currently privileged. And the process tends to be that when you invoke the exploit, Metasploit will examine the target system and say, are you available? Is the system currently vulnerable to this exploit before we go ahead? And if it passes all the checks, what it then does is it will probably spin off a separate application instance like notepad.exe. And that notepad instance is hidden from the user. And then it will upload a DLL that contains the exploit, and that DLL is reflectively loaded into the new notepad.exe process. So we've got a process here that launches Notepad. This process takes a copy of a DLL. It then inserts it into the memory space of the running Notepad, not touching disk, and then it reflectively loads it. So there's a process called reflective DLL injection that's invoked at that point. And when that's invoked, the DLL spins up. So what you're seeing on screen here, this DLL main that I've just highlighted, that is the entry point to the DLL as soon as it has been reflectively loaded. Now what you're seeing on screen here is a very similar sort of stub to what happens in every single MSF privilege escalation exploit. There is one key thing to remember. When the exploit is invoked, Metasploit, as you know, allows you to specify what payload is to be run when the exploit succeeds. So that exploit, the payload can be like shell reverse TCP or Meterpreter reverse HTTPS or something similar, something that matches the target platform. In order to be able to specify those payloads, what we want to be able to do is we want to be able to upload the DLL, and then when we invoke DLL main, we want to say, here is the shellcode I want you to execute when the exploit is deemed to be successful. So you'll notice here, this DLL main, when it's invoked with process attach, which is what happens after it's been reflectively loaded and the exploit is then run, we get passed in a parameter here, a pointer to an area of memory in LP reserved, and we know that MSF is going to give us that as a pointer to the area of memory that contains the shellcode. And so what we do is when we attach, we just say, right, we're going to run our CAPCOM.SYS exec function and pass in a pointer to the payload. And this here is the function that gets invoked. Now, this includes all the reflective loader stuff that we need in order to turn it into a reflectively loadable DLL. This kernel include is that header file that includes the kernel related stuff I've already mentioned. And this is just a little helper stub that says, here is a pointer to an area of memory. I want you to execute it as if it's a function. So you can see it's just typecasting it using horrible C syntax to a function pointer and then invoking it as a function pointer. That's where our shellcode actually gets run. So the interesting part here is this. This is where we're going to be inserting what we've effectively just done. Okay, so step one, we're going to take what we know of the existing function that we use to exploit the binary on the target, and we're going to re-implement it here. Okay, it is a little bit tedious, but I think it's worth going over it again. I've got my reference over here so that I can type it out a little bit quicker. So to start with, we're going to start with our const dword, which is a magic IOCTL value, which is the hex AA013044. So that's our constant we're going to be using for when we're dealing with our IOCTL. And we're going to need a handle to the driver, which will start as invalid handle value. Next, we'll do our classic do while 0, so that we've got an easy way of bailing out. And if the driver at this point is not invalid handle value, we're just going to close handle driver. So One of the habits I have is when I'm referencing variables that are going to contain resources during the course of my coding, the first thing that I do is put cleanup code in the relevant point, and then I don't have to think about it again. I'm going to be slightly dirty here. Instead of declaring a constant variable, I'm just going to do a create file. Now what I'm going to do is call create file A, which forces the use of the ASCII string version rather than using create file that maps to a macro depending on compiler settings. So that means I can just type it in like 1234.12. What was it called? HT system 72FB. Okay, so that's the name of the driver we want to talk to. Generic read and generic write are the flags that we're looking for. The share mode and the file share read and file share write. I'm going to null for security attributes. Creation disposition, what was that again? That was open existing. Flags and attributes, what is this one? File attribute normal. So again, we're just creating a device driver handle. So if the driver ends up being invalid invalid handle value, we're just going to break it. Simple as that. Okay. Just make sure that I've got your feed up here so that we can see. Okay, so we've just created an instance of our driver. Next, we're going to do the creation of the template. So we've got a byte array. I'm just going to call it template. Oh no, I can't use a template because this is a keyword. Let's call it. We'll just call it a payload template, which is a binary array. Okay. Again, we're just going to use exactly what I did before. So let's go OX, OO, comma. We're going to need 8 of these. So 1, 2, 3, 4, 5, 6, 7. Oops. We'll get some Vim magic happening. Pointer to the start of the shellcode. Also have a pointer to the steal token function. Here we're going to have our 58 OX 08 1, 2, 3. Call relative jump plus 8 to skip the token function pointer. Some documentation in here that actually makes a little bit of sense. Next we're going to go hex 58, which if everyone can remember is pop racks, because that's going to give us our return. Finally we're going to go ff OX20, and that's going to be jump 2 racks. Now we use the jump instead of a call. It's probably worth noting we're using a jump instead of a call because until now the call that was invoked by the device driver has set up all the parameters to handle a call appropriately. If we use call, then we'll end up with another return on top of the stack frame. So instead of using a call, we just want to jump past control, and then the return of that function invocation will actually return to the thing that called this particular function. Okay, so what we're also going to need to do is we're going to have a, we'll call it the input buffer again, and here we're going to set it to null. And over here we're going to say if input buffer is not null, so if it was successfully allocated, then we're going to call virtual free on the input buffer. Okay, so that's again me just tidying up after myself because I don't like leaving a mess. What have I done here? Ah, right. Address size. Do I really need the size? Really? Do I really need the size? It should know. Let me just quickly check some documentation. virtual free says give it the size of the region. If the free type parameter is member release, the parameter must be 0. Yeah, okay, that makes a bit more sense. So we're just going to give it a size of 0 and we're going to go mem release. So what we're saying is we're going to mark that area of memory that was allocated as released. Sorry about that, I forgot those two parameters were required. Okay, so our input buffer is going to be that needs to be a pointer to a byte, not just a byte. So p byte virtual alloc. We don't care where it's mapped to. We're just going to say give us the same size as the payload template. Allocation type is mem commit mem reserve, and we're going to have page execute or read write. So it's a classic case of give us all the permissions on the block of memory. If the input buffer fails, so if it ends up being null, then clearly we want to bail out. So we're going to break again at this point. Otherwise, let's copy, oops, moving too fast for my own good. Let's copy to the input buffer from the payload template, size of payload template. Okay, and then from there we just need to do a little bit of pointer dancing. So pointer to an unsigned long pointer. We'll cast our input buffer start, and we're going to set that to whatever the ulong pointer value of the input buffer far out plus 8 is. Okay. Then from here, as we remember, we've got to offset 13 from there, and we're going to set that to steal process token. Okay. So with that in mind, we should be able to do device IO control, pass in the driver handle, or actually we need to also do the dword result buffer. We'll set that to 0. Dword bytes written is also 0. Okay. So first off, control code. That's going to be our magic IOCTL value. Next, our result buffer. Hang on, where are we? Result buffer. Result. That's not what I'm looking for. Yes, it is. Should learn to type. We also need a ulong pointer, which is the target, and that needs to point to ulong pointer input buffer plus 8, as we had before. Okay, so from there, we give it the address of target, and we say we're only giving it 8 bytes, even though the buffer is way bigger. The output buffer is going to be result buffer, and we know that's going to be 4 bytes. Bytes returned will be bytes written, and null for the overlap call. So from there, we should be able to say if was token replaced, execute our payload that we've been given, and boom, that's it. That should be it. If this builds and runs first time, I'll be pretty happy, because it's not exactly the same as what I have here. Anyway, so hopefully this looks familiar based on what it is that we just did on the other machine. When I build this, you'll see here, external source exploits CAPCOM.SYS exec release blah. So that generates the DLL, but then a file is copied. So if we go back over here, you'll see that we actually have in the data exploits CAPCOM.SYS exec CAPCOM.SYS exec x64 DLL. That's the payload, that's the reflective DLL that is now going to be reflectively injected into the target process. Let's have a look. Questions? Any questions, anyone? Ah, Norse is here, and Miles. Welcome, chaps. Okay, so what we're going to do now is we actually need to start working on our we need to start working on the Metasploit site. So this is my least favorite part because it involves Ruby. However, we do have some bits and pieces in place that we can use to effectively reduce the amount of shit that we have to worry about by copying and pasting an existing module, which I know does basically the bulk of the shit that we've done in the past. So let's copy modules exploits Windows local MS15 no 51 client copy image. And what we're going to do, because this actually doesn't have any detail associated with it, we're not even going to prefix it with a CVE or an MS number or anything like that. We're just going to call it CAPCOM.SYS exec.rb. Okay. All right, let's load this up in our favorite editor. Okay, so to begin with, what I'm going to do is I'm just going to modify the existing doohickey so that it contains some interesting information around whatever it is that the exploit does. So we're going to go Windows, I'll call it CAPCOM.SYS driver code execution exploit, and I'm going to mark it as 64-bit in the description so that we can see it. This module abuses, I'm not going to say exploit, this module abuses a feature in the CAPCOM.SYS driver for Windows that allows for userland code to be executed in the context of the kernel. This driver deliberately disables SMAP prior to, oops, I should get rid of the comma, prior to invoking code, and that should be it. What I'll do is I'll say this module has been tested on Windows 7 x64. It should work on earlier versions too, but will not work on Windows 10 at this point because this exploit does not contain a bypass for SMAP. It should be coming later. So there is a plan for me to tag team the SMAP bypass stuff with Justin Stephen, my partner in crime. We're going to get together and we're going to actually get this thing running on Windows 10, but Windows 10 has other features built in that prevent this kind of thing from happening. So what I'm going to do is I've got a list. What's the dude's name again? Let me scroll back through the chat log because that'll tell me. I'm sure I'll posted the link. What's his name? The Wackolian. So credit where credit is due. This is very important. Was is it CK? CK-Olian. So we're going to start with issue, discovery, and publication. And exploit. Always put the people who discovered it first because they did the hard yards. So, now that we've got some basic shit out of the way, the architecture that we've got listed here, as you can see, the current version has x86 and x86-64 support. Now the module we're creating is only 64-bit. So I'm going to get rid of the x86 option. Now I'm pretty sure that x86 will actually work, but I don't have the driver and I can't validate that it'll behave. Okay, so we're just going to have 64-bit. It's a Windows platform related thing. We're going to rely on Meterpreter to do this because we have to do some other magic like reflected DLL injection, etc. By default, you'll see that exit func is set to thread. Now, I think I'm going to change this to process, because we will actually create a new instance of Notepad to host this exploit in. And so when the thing finishes, we actually want it to tear Notepad down. We'll get rid of the x86 target because we know that's not going to work. We'll leave space and disabled NOPs as they are, even though they're not relevant to this exploit. There's a pattern here that's in use, and I'm just going to leave that be for now, and we'll talk about that maybe another time. I currently only have one reference, and that is the, hang on, where are we? That is the tweet. So let me just dig up the link again from the chat log. Contains the tweet. Come on, where are you? Where are you? Ah, Justin, mate, thanks for the heads up. I didn't know that. So, yeah, okay, so it is actually only going to be 64-bit. Fascinating. Your timing is impeccable. I just gave you a shout out. I'm just going to repost this link because I'm lame and still don't have it somewhere. Copy link address. Thanks, Ben. You're a legend. Got one. Cheers, buddy. Copy link address. Gotta love that. Got enough dude, isn't he, champion? Okay, disclosure date doesn't exist, so I'm just going to delete it. Now, in the name of expediency, I'm just going to get rid of the check, and we're going to come back to that later on. But what we're going to do here is we're going to be partly lazy and partly not. So, to begin with, if the current session's already elevated, then we're not even going to bother doing the exploit. That's a bit silly. We can get rid of this check result equals check because that just seems rather superfluous. We'll worry about that a little bit later on when check actually fails, or doesn't fail, shall we say. Well, then again, when the default check method actually returns whether it's valid or not. So let's leave that in. So the check result equals go ahead and perform a check method to see whether or not the thing actually is vulnerable. We'll fill the check method in a bit later on. So we'll leave this default thing here saying if it's not safe, if it is safe or it's unknown, then we'll just say no, we're not sure that it's available on the system. We're going to leave WoW64 check in here that says running against WoW64 is not supported. The reason for that, even though it technically would be, is that if you're running a WoW64 interpreter, you're actually 32-bit in a 64-bit land. When you create new processes like Notepad, you have to make sure you spin up the 64-bit version, and then you have to do some horrible remote thread creation shenanigans in order to get a remote thread running after you've reflectively injected the 64-bit DLL into a 64-bit Notepad from a 32-bit process. So doing all of that directly from inside Ruby is actually very painful. So what we do instead is we say running against WoW64 is not supported. That basically means you need to go and either spin up a 64-bit version of Interpreter on your target or migrate to a 64-bit process. Session host is 64, but the target is specified as x86. Now, that technically can't happen because we haven't specified x86 as a valid target, so we're going to get rid of that step there. Also here, if the current architecture is x86, then clearly we're not going to allow that either. So whether or not we're running as a 64 or 32-bit interpreter, if we are running as an x86, and the session host is x86, but we'll say the exploit is, let's say, specific to x64. Okay, so at this point, what we can do is we're launching Notepad to host the exploit. That's just the magic to do that behind the scenes. Then what we're going to do is we are reflectively injecting the exploit DLL. Now I wrote this module ages ago, so I know how this process goes. You can see it says we're going to inject the target exploit DLL. Now we know that the architecture is going to remain the same, so I'm just going to get rid of this line here and instead of that CVE, this is going to be CAPCOM.SYS exec, because that's the folder that the exploit's in, and it's called CAPCOM.SYS exec.x64.dll. Okay, so we might even tidy that up a bit and chuck it on the next line. So we generate the location of the DLL locally on disk. From here we expand that path locally so that we know exactly where on disk that is. We inject that DLL into the target process using some helper libraries. From here we then say, right, I want to inject the payload into that target process, right? So this puppy here is taking the payload, right? So we've already got the DLL here, that's in memory. We're then taking the payload that the user specified, reverse Meterp, reverse TCP, bind TCP, whatever the fuck it is. And then from there, this is the magic line here. So we say create a new thread in the target, and we're saying invoke this area of memory, which you see how it says exploit mem plus offset. What that's saying is the offset of the reflective loader function, and go. And then from there, give it the payload memory pointer. So that's the value that gets passed in. Let's go back here. The value that gets passed into LP reserved, which ends up being the payload that this thing runs. Yeah? That is what is being passed here as payload mem. Now we know, based on the fact that we have injected this stuff into the process, that the memory has been mapped as read, write, and executable. Okay? So that's all very exciting. Moment of truth. Right, let's just quickly duck over here. Go to our Corlan machine. Now I've deliberately set this up so that it has a listener, sorry, a interpreter payload that when I run is going to connect locally. I'm going to run this from the command line. You'll see here it says MSF console-x. Use multi-handler, set payload, Windows x64. So all I'm doing there is setting up a payload, a handler to receive the payload. This is all done on the command line, so I can easily restart stuff. Because I may well have messed up with my module definition and it may not actually work. Alright, so MSF is spinning up. There you can see I've actually got a reverse handler listening on port 8000. Let's go back over here and we'll kick off our session. So here you can see I'm currently running as this pleb user OJ, and I've got a 64-bit Meterp. My missus is awesome, isn't she? Okay, so what we're going to do is we might actually just fly by the seat of our pants. Let's go use exploit Windows local CAPCOM.SYS exec. Okay, so it's all there. We'll set session to 1. We'll go set, what payload should we have? Let's start with something simple like Windows x64 shell reverse TCP. Set lhost, whoops, 10.1.10.40. I'm going to change L port to something else. Okay, moment of truth. Let's see what happens. Nothing! Ta-da! Did we crash it? No, we didn't. But that's okay. Now, let's see if we can figure out why that's happened. So, oh! I know why. I'm guessing that the driver hasn't been set up. So what I'm going to do is sc start Capcom. Oops. Oh, that's right. I need to actually restore this to a particular snapshot. Okay, so I did what I did before. I had the driver installed, set up, configured, ready to go. but I didn't revert to the snapshot. Let's get rid of all the sessions and we'll start again. So that's literally because the driver was not loaded. Of course it's going to fail. Now our check method is going to change that. So let's set our session 4. Come on, do your thing. Blue screen, yeah. Nice. All right, let's go back to how it was before and we'll figure out what it is that we've done wrong. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8. So we do have an 8-byte pointer. Here we've got a call followed by a 4-byte amount. We've got another 8-byte pointer. We're calling pop racks and we're calling jump racks. So that should all be good. We're then copying from the payload template over to the input buffer, which we have allocated based on the size. So that all seems legit. From here we're saying set the start of the input buffer so that it points to the next 8 bytes. We're then saying make sure that we set the steal token function pointer to the steal process token. We then point this little target at the offset into the input buffer. The result buffer is set, the bytes written is set, and we pass in that value to the driver using the magic IOCTL. Now let me just see, I'm going to quickly reference my existing function to make sure that I haven't done anything stupid. Because I do have it jotted down. 58, 508, that all looks fine. Maybe I need, no, that shouldn't be so much of a concern. I had for some reason I put a +1 in here. Commit, reserve, execute, redrive, payloads not break. And copy size of the template. Okay, that's should probably just make sure that doesn't equal null, but I can't see that being a concern. So let's have a look. I know, disappointed. I was hoping it was going to work first time. So close, so close. This went down really well. So yeah, I can't see anything immediately obviously wrong about this. So maybe we're going to have to add some debug output or try and figure out exactly which blob is causing the problem. Oh, hang on. Is that what it is? Result? No, that's not a problem. Yeah, so I didn't have this result buffer before. I just had write it back to the input buffer location. But again, that's not going to work. So we've got target 8, input buffer 4, address bytes written null. We just make sure that that's set to commit, reserve, page execute, rewrite. Set the input buffer to that. Yeah, I don't know why that killed it. That's very strange. Set session 6. Our first session is dead, so let's kill it. Let's see if we can see it. It's blue screening in real time. Yeehaw. Okay. So what am I doing wrong? I'm doing something very silly, there's no doubt about that. Give me a sec. Okay, so just going to quickly do check. Make sure that I'm not doing anything majorly stupid. It's clear that I'm actually getting to the point where code execution is happening, which leads me to believe that as a result we're seeing blue screens. But for some reason, when the shell code executes, it's not doing what is expected. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's definitely 13 for this. That should work without concern. That's definitely correct. Like we were doing before. Target's definitely correct. Bytes written is definitely correct. It's hard to see what's wrong with this. Pop racks, jump racks. You're watching me fail. I bet it's making you very happy. Oh, yeah, I know what's wrong. If you don't prepare for the kernel, break. Okay, so the reason why that was failing is because the token stealing shellcode was relying on function pointers existing. That didn't exist. Ha! What a numpty. Let's just quickly restore. It's alright, I got it. I got it, it's all good. I know what I'm doing. Hey! Buster B. Cook's here. This is for those who don't know, Buster B. Cook is Brent Cook. And he is a machine. He's the guy he's a Libra SSL committer. He's head of engineering on the Metasploit team and is the guy who has is basically the wingman for Metal, the new POSIX payload. He is incredibly humble and is a fucking machine. So if you don't follow him already, you should totally follow him because he's awesome. Okay, so let's kill that off. Spin up a new one. Okay, so now we've got a session. So we'll set that session to 8. I did build that, didn't I? Now I'm paranoid. I'm paranoid. Build. Run. Come on. Blue screen. Bollocks. Okay. Let's see. If we don't prepare for the kernel. We should also probably go if the driver. This is something that that I put in a little while ago. If the driver isn't loaded, so CAPCOM.SYS. If that's not loaded, oops. So if the driver's not there or preparing for the kernel isn't there, then we'll bail out. What we clearly are missing is proper friggin' avoidance of failure. Them plugs. Okay. God, I thought my whole machine had frozen then. That would have been very bad. Okay, so it's time to cheat. Let's close this off just for a sec. I'm just doing something off screen for a sec, just bear with me. copying over a version that worked before. In the hope that this is actually going to resolve the issue, because I don't want to waste everybody's time. Let's go main. So this is one I wrote earlier. Where is it? Oops, don't know what I did there. Sorry. Modules, exploits, local, CAPCOM. Sorry. I'm failing in all manners at the moment. Yeah, okay, so close that down. Okay, so go back. Everything here looks fine. Source. I know this is probably boring because nothing magical is happening on screen, so forgive me for that. Alright, let's go back in here just for a minute. So this is one I had written earlier, which I know works. Which is pretty much exactly the same, just with some different commentary. So let's clean that, rebuild. Yeah, I don't know what happened there, but given that it's 10:30 and getting pretty close, I want to have this finished up soon. So hopefully this will save some of my fucking sanity. Okay. Ah! Boom! There we go. Okay. Why that wasn't working before, I honestly don't know. But if you look through the code here, you'll see it's pretty much exactly the same. I'm checking to the driver, checking, preparing to the kernel. I can get rid of these debug strings, which I had in there before. This is all pretty much exactly the same as it was. There's the payload template, virtual alloc, making sure it's all set to null. In fact, the only thing that's missing, ooh, I wonder if this is it. If payload doesn't equal null, virtual free payload 0 mem, what was it called? Where's my documentation? Mem release. I wonder if that's what's killing it. So, payload, which is here. As you can see, IntelliSense is well and truly screwed. What have I done now? What do you mean undeclared? Oh, I should probably put an L there. No. Okay. Let's see if this is what it was. That'll be annoying, hey? Back to 1. Let's exit out of that session. Yeah, there you go, it does work. Alright, so set payload Windows x64 interpreter reverse TCP. What have I done? Interpreter. So we'll keep it all the same, and let's see what happens. Different payload. Anti-authority system. You beauty. Okay, sorry about that. So as you can see, like, the process is actually fairly simple. Hopefully all of this stuff in here is at least relatively self-documenting. What I'm going to have to do now is add this bit here that does the check. Make sure that we, number one, see if the CAPCOM driver is installed. Number two, make sure that the architecture matches, all of that kind of stuff. So, given that I promised to get something in that was ready to be checked in, we should probably undo this crap here. So we want to make sure that it's Windows only. The architecture can be WoW, it can be x64. Excuse me. Otherwise, we should probably return safe, because we know that the 32-bit versions are not vulnerable, certainly not as far as this exploit is concerned. So what we're probably going to have to do is look for the CAPCOM driver somewhere on disk, or perhaps figure out a way of enumerating the driver remotely, which I haven't done using Metasploit before. So yeah, this should be fun. So the question is, whereabouts is the CAPCOM driver actually installed to? And if we can't do that, is there a way of saying enumerate all of the drivers on the system and see whether or not the CAPCOM driver is loaded? Now, we certainly can do the latter without checking the version, but I'm unsure right now as to whether or not whether or not the target actually has the system file, the driver file, in a known location. So what we may have to do for now is, okay, so if it's not Windows, we also should probably for now put Windows 7. I don't know if this works on Windows 8, so let's just say rather than unknown, because no, we'll leave it as unknown. We're just going to leave it as Windows 7 at this point, because we know that it works on Windows 7, and then later on I'll update this to include Windows 8 targets if Windows 8 actually works. Need to validate that it behaves itself appropriately because of that SMAP issue. I don't know whether that's enabled or not on Windows 8. So if any of you guys know the answer to that, that'd be good to know. Otherwise, I might just leave it at that. So if it's Windows, we're going to assume that if it's Windows 7, that it may be vulnerable. Now I'm going to get rid of this stuff, because that's clearly looking at a version of Win32k.sys, which we don't care about in this particular case. So what we should probably do here is a to-do check for the CAPCOM.SYS driver and version. Now down the track, apparently the Capcom people are going to be updating updating the Capcom driver so that this security feature goes away. However, yeah, so we'll probably have to check what the current version is and then match that later on. But for now, I'm not going to do that because I don't have access to that information. So yeah, that's pretty much it. Let's just quickly check to make sure that works still. Yay. What's that, Ebox? You've sent me a link to something. Ah, okay, so it's in Windows System 32. Okay, thanks, Evox. That's really helpful, man. Actually, let me just take that and we'll view him directly and we'll edit code, Metasploit framework, modules, exploits, Windows, local, CAPCOM.SYS. Okay, so post file. So what I need to do now is do exactly what I have just deleted. So that wasn't very smart, was it? So let me just copy that back. Bear with me while I locate all the things. What was it called? 15051. Okay, so just grabbing the exact line of code that we've just checked against, and we'll do exactly the same thing. Exploits, Windows, local, and that's 15051. Alright, let's paste this back in. Windeer, System 32, CAPCOM.SYS. Okay, so CAPCOM.SYS file version. Okay, so we can get the file version out, which is cool. And the question is, what is the file version? I don't even know. Let's have a look. Details. Are you kidding me? Way to go. Way to go, Capcom. Love your work. You fucking morons. Okay, so this thing apparently doesn't have a version. It's signed, but it has no version. Okay, alright, fuck it then. If the file exists, we're just going to say it appears to be vulnerable. How about that? I don't remember what that piece of code would look like. Just quickly grepping for it. File. So I'll pull out the piece of code that checks to see if the file exists in a remote session. So you've actually got to do this via Meterpreter. So let's see. File exist. That's pretty much what it is. We'll leave file path like that, and we'll go return exploit, check code, safe, unless file exist file path. Otherwise, we'll say that it's there. Okay. So that means rerunning the exploit here. What does this say? Exploit not available on this system. Really? Is that because I added Windows 7? Probably is. Nope. Let's go file. Let's just output the file path. This is me doing my classic printf debugging. Let's go. Just see what it says where we got to. Okay. I should probably use double quotes, given that it's Ruby and double quotes are the only ones that support it. So clearly I didn't get here because file exist failed, which is expected because I'm actually running the exploit from a non-standard location. So for the sake of testing, I'm going to do I'm going to change this to $C and we'll exploit that. C, put system32, what am I doing? Okay, so that's actually doing the check, and if it's there, it works. Okay. I will change it later so that it does exactly what it should do, and we'll run the Capcom driver from system32 instead. Thanks, Evox. That was pretty helpful. Yeah. Thanks, guys. You picked up on my fail before I did. So what I'm going to do is I'm going to leave it as that for now, and maybe we'll refine this a little bit later. Well, let's exit out of that. So I'm going to run it again. So of course it's going to be not working on the system. What am I talking about? So what I need to do is this kind of stuff, so that I can copy and paste that into what will become our Metasploit framework pull request. So this is the final part. Okay, so these are all the files. Hopefully everything works as expected. We actually are going to commit binary here. So I'm going to go git add all the things. And just make sure that we've got the DLL, the git ignore, the solution, the C file, ms build. This make.bat, as I said, is like a build all the exploits from scratch. Some helper kernel related bits and pieces, and the module itself. So let's actually put something decent together. Add exploit module. Actually, we should say LPE exploit module for the Capcom driver. Capcom driver. Let's call it a floor. This commit includes, I like to put this inside commit notes, RDI binary that abuses the smet bypass and userland function pointer invocation that is provided by the driver. Related Metasploit module, updated build file, and associated make.build to build command line. In fact, I might reverse those. Okay. This also includes the beginnings of a new set of functions that help with the management automation of kernel-related functions for kernel-related that help kernel-related work. It's probably a better word. On Windows or local DOS exploits. Did I type that right? Okay, so git push origin. So I'm pushing this up my local branch, and I should be able to refresh this, and it should say Give me the big green button. So I push that to my local branch, so git push origin CAPCOM.SYS exec, which is the current branch that I'm on. And then when you go to GitHub, it should give you a big fat green button that says create a pull request. For some reason, I don't have that, so go to my own fork. Branch CAPCOM.SYS exec. You must be that'd be why. Okay, so you can all witness me using LastPass with my multi-factor authentication. There we go. Now if I go back here. Yeah, shut up. Shut up, Hellies. Shut up. Okay, so add LPE exploit module for CAPCOM driver floor. So let's just add some very basic stuff. This module implements this PR includes code that exploits the feature provided by the CAPCOM.SYS driver for Windows x64 that allows for userland functions to be executed in the context of the kernel. The exploit has only been tested on Windows 7, but should work on earlier versions or any other version that doesn't have SMAP support. As I like to do, a sample run and just dump a bunch of code, output that comes from one of these. So I'm going to do this and paste that in. So that should show that everything worked just fine and we ended up with a system shell. From here I'm going to get rid of all that crap and I'm going to say verification. And this is where the fun verification steps come in. We're going to say create a handler that can receive an x64 interpreter, Windows interpreter payload, create matching payload, create or locate a system that has a Windows x64 system that has the CAPCOM.SYS driver installed. Run the interpreter payload on that system as a low privileged user. Verify that the session connects. Run use exploit. Oops, can't type. Windows local CAPCOM.SYS exec. Set the payload to any of choice. Set the session to that was created on the target system. Run exploit. Verify that the resulting session is running under the context of the NT authority system. Okay. There we go. It's pretty simple stuff, right? What I might do is just put more information. All began thanks to. Let's get that tweet reference out again. Scroll, scroll, scroll. Oops. Okay, so there's our sample run, details of verification, references. We should also say this is related to Meterpreter and it's a module. And at this point we should be able to go create pull request. And there it is. We're done. Thanks for sticking with me. There were a couple of little painful bits in there, but I hope you guys learned something from it. You can go and read the code now of your own Volition through this 7363 GitHub link. In fact, I'll paste it right here so that you guys can check it out if you want to. If you have any questions, then you can hit me up directly. You can talk to me on the IRCs, on the Twitters, on here. You can give me comments, abuse, whatever the hell it is you feel like. Thanks so much for sticking at it. I hope you enjoyed. So, given the time, I'm going to sign off. Cheers for your support. See you guys later.